Hi, this is the chapter 12 quiz practice. These are for problem. So in problem 1, we have when 84 grams of iron 3 oxide reacts with an excess of carbon monoxide, iron is produced. And make sure you have the right version of this because in one of the versions I sent out, it was carbon dioxide on both sides, so it needs to have carbon monoxide right here. So our first step is a balanced equation, which we have here. Our second step is to figure out what we're doing, what we're trying to solve for. So we have 84 grams of Fe2O3. We're trying to figure out how many grams of iron is produced. All right. And that's our theoretical yield. That's just another way of saying how many grams of iron is produced. 3 is we want to make our grid. And before we do our grid, let's remember that we need to figure out the molar mass of a couple things. We need to find the molar mass of iron off the periodic table and the molar mass of iron 3 oxide, both of those. So the molar mass of iron is 55.85 grams per mole, and the molar mass of iron 3 oxide is 2 times 55.85 plus 3 times 16, which ends up being 159.7 grams per mole. Okay, we're going to need those two numbers for what we're about to do. So that's for step 3. So let's start with what we're given, which is 84 grams of Fe2O3 in our grid. If you look at your double mole map, if you follow along, we're going from grams to moles. So we have 1 mole of Fe2O3 over 159.7 grams. The third part of our grid, we're going from moles of Fe2O3 to moles of Fe. So 2 moles of Fe over 1 mole of Fe2O3. And that comes from here. We have 2 moles here, and we have basically an invisible 1 in front of that Fe2O3. And then we use our molar mass of Fe. So 1 mole of Fe has the mass of 55.9 or 85 grams. And then step 4 is plug and check. So 84 divided by 159.7 times 2 times 55.85. And our answer is going to be about 58.75 or 58.8 grams of Fe. Okay? That's the answer there. So step 2 says when 5 grams of copper, I apologize for any screaming here in the background, when 5 grams of copper react with excess silver nitrate, silver metal, and copper 2 nitrate are produced. So what is the theoretical yield of silver in this reaction? So what we're going to have to do is write an equation for copper reacting with silver. Okay, so we have copper metal. Okay, so copper metal plus silver nitrate, okay, which is aqueous. Silver has a +1 charge. Always, it's one of those 3 transition metals that has a consistent charge, and nitrate is NO3 minus. So because those 2 ions have the same magnitude of charge, they can just go together. And then copper is more active than silver, so it can push it out of the compound, and what we get is silver metal plus copper 2 nitrate, so NO3 2, because copper is a 2 plus charge and NO3 is a -1 charge, so we have to use a little shroopy there. And this is aqueous. So the copper has dissolved into solution and silver has precipitated out of solution. Now this is a single replacement reaction. For those of you who guessed that, great job. The reaction's not balanced, right? We have 1 copper on the side, 1 silver, and 1 nitrate, and on this side we have 1 silver, 1 copper, and 2 nitrates. So in order to make it 2, we're going to put a 2 right here and a 2 right there, and now it's balanced, okay? So now we're going to perform the calculations to determine the theoretical yield of silver in this reaction. So we're going from 5 grams of 5 grams of copper, 2 grams of silver. Okay. So start our grid with 5 grams of copper. Our molar mass of copper is 63.5 grams, 1 mole. Okay. And now we have to look at our equation, our balanced equation, and there's this invisible 1 in front of copper, and there's a 2 in front of silver. So 2 moles of silver, that's the ratio here, to 1 mole of copper. And now what we need to do is have our molar mass, so 1 mole of silver to 107.87 grams of silver, okay? And now step 4 is we're just going to plug and chug. So 5 divided by 63.5 times 2 times 107.87 equals 16.99 or 17 grams of silver. Okay, great. So moving on to number 3. This is a limiting reagent problem. So we have to figure out which one is our limiting reagent. Okay, so in this problem we have iron sulfide and oxygen are reacting to form iron 3 oxide and sulfur trioxide. And if we start with 20 grams of iron sulfide or 16 grams of oxygen, which one is our limiting reagent? And then how much sulfur trioxide would we produce? Okay, so to get started, let's find what our molar mass is of our iron sulfide. And this is iron 4 sulfide to be exact. Iron is going to have a +4 charge here. And the charge of our oxygen. So 2 times 16 is 32 grams per mole. That's the molar mass. And this iron 4 sulfide is going to be 56 is the molar mass of our iron, plus 2 times 32. And so our molar mass is 120 grams per mole. Okay. So in order to do this, we're going to convert both of these. Okay, these are our starting ingredients, if you will. We're gonna convert both of these starting ingredients to grams of SO3. We need a molar mass of SO3 too. And so our molar mass of SO3 is 32 plus 3 times 16, which is 80 grams per mole. So we're going to convert both of these starting ingredients to grams of SO3, and we're going to see which one produces less, because that will be our limiting reactant, and that will be the amount that we produce. So 20 grams, so we're doing 2 stoichiometry problems. 20 grams of iron 4 sulfide. I'm calling it iron 4 sulfide, by the way, because that means the iron has the charge of 4. Okay, 1 mole is 120 grams. Okay, now we have to use our mole ratio. So 4 moles of FeS2 over 8 moles of SO3. And now we're going to use our molar mass. So 1 mole of SO3 is 80 grams. Okay, and if I plug and chug 20 divided by 120 times 8 over 4 times 80, what I'm going to get is 26.66 grams of SO3. Okay. So now if I do oxygen, I have O2. 1 mole of O2 is 32 grams. Oxygen's diatomic, obviously. We have 15 moles of O2 are needed for every 8 moles of SO3. That's our ratio. We're getting those numbers from the equation up there. Those are the coefficients. See, 8 and 15. And 1 mole of SO3 is 80 grams. And when we do this calculation, so 16 divided by 32 times 8 divided by 15 times 80, we get 21.3 grams of SO3. Okay, now if I look at these two, okay, this one is less. All right, So 20 grams of iron 4 sulfide will make 26 grams of SO3, but 16 grams of O2 will only make 21 grams. And so since this is my lower number, then this oxygen is my limiting reagent, right? You can't make any more because I only have 16 grams of oxygen. Okay, so this is the amount that's made. That's my theoretical yield. This is my theoretical yield. If I did everything perfect doing this reaction, that's how much I would get out. Okay, so oxygen and O2 is limiting. A limiting reagent or reactant, and it means that iron sulfide is in excess. Okay, a little bit left over. So the last problem says rust is produced when iron reacts with oxygen. Okay, how many grams of, oops, there's a little mistake here, iron 3 oxide are produced when 12 grams of iron rust. So this is a basic, straightforward stoichiometry problem. I have a balanced reaction. I'm going from 12 grams of Fe to grams of Fe2O3. I need my molar mass of Fe2O3, which I looked up before for the first problem, and it's 2 times 55.85 plus 3 times 16, and I get 159.7 grams per mole. Okay, and so I'm going to set up my grid, and I have 12 grams of Fe. 1 mole of Fe is 55.85 grams. I have 2 moles of Fe2O3 over 4 moles of Fe. I'm getting that from my equation, obviously. 2 moles of Fe2O3 over 4 moles of Fe. And then 159.7 grams is the molar mass of 1 mole of Fe2O3. And I haven't been doing this in the other problems, but you can certainly do it in yours. You can make sure that your units cancel. So grams of Fe cancels, moles of Fe cancels, moles of iron 3 oxide cancels, and what I'm left with is grams, which is the unit that I want. So now step 4, I'm going to plug and chug. So step 4, I'm going to plug and chug 12 divided by 55.85 times 2 divided by 4. Now obviously this is the same thing as divided by 2, but I'm putting it all in there so you see my little my math trail, and 159.7. So if I plug all of that in, I get 17.16 or 17.2 grams of Fe2O3.